that we know how to draw the sub-level electron configuration like we did in the previous flip lesson, and that's these three examples that we did from the previous flip lesson, which is silicon, manganese, and argon, I'm now going to show you how to write what's called the Bohr electron configuration. Now, this might seem like a little bit of a throwback to middle school, and it is. And to a lot of students, they go, once you learn the sublevel configuration, a lot of them ask, why do we have to learn the Bohr electron configuration? Because it seems like there's less information in the Bohr electron configuration than in the sublevel configuration. The answer is you're really kind of responsible to know both methods, because there is some use in the Bohr electron configuration, which I'm going to get into in our next units that we have on chemical bonding and things like that. So what exactly is the Bohr electron configuration? Well, if this is the sub-level electron configuration, so the three examples we had in the previous flip lesson, the Bohr electron configuration is an electron configuration in which only the number of electrons at each principal energy level are written. So it's actually pretty simple, and it's going to be a little bit of a flashback from middle school. Here is the sub-level electron configuration for silicon, and remember that the big numbers in front of the letters that tell us the principal energy level of that sub-level is inside of. So we have an S sub-level in the first principal energy level, and the second we have an S and a P, and then the third we have an S and a P as well. So looking at just the first principal energy level there, which I put the green box in, we have 2 electrons in the first principal energy level. So our Bohr electron configuration starts with a 2. Then in the second principal energy level, well, we have 2 sublevels, the S and the P sublevel, for a total of 8 electrons, 2 in the S and 6 in the P. And then in the third principal energy level, we have this 3p sublevel. It's not completely filled up yet. So we have only 2 electrons in the 3s and 2 in the 3p for a total of 4 electrons in the third principal energy level. So the Bohr electron configuration for silicon is 2, 8, 4. And if you remember anything from middle school, is that these are the number of dots you would put on that ring that goes around the nucleus. So if I wanted to draw the Bohr model of the atom, and I left off the nucleus that would be in the middle here, so you don't confuse it as an electron as being another dot, we have 2 electrons in the first ring, 8 around the second ring, and then 4 around the third ring there. And those are the different shells of electrons around the silicon atom. Now for manganese, things are a little different. It starts out pretty much the same because there's a completely filled 1s sublevel in the first principal energy level. So again, the first number of the Bohr configuration is going to be a 2. And then also with the second principal energy level, a completely full 2s and 2p. So we have a total of 8 electrons in the second principal energy level. It's the third principal energy level that gets a little tricky. Now remember, there's then overlap. According to the diagonal rule in the Aufbau diagram, the 4s sublevel has less energy than the 3D. So the third principal energy level is the S, P, and D sublevel here, even though there's this S right there in the middle. And so we have a total of 2, 6, and then 5 more electrons, which gives us a total of 13 electrons in the third principal energy level. And then in the fourth principal energy level, well, we just have those guys in the 4s there. That's completely full. And so there's 2 electrons in that fourth principal energy level. So if we wanted to draw the Bohr model of the atom, there would be 4 rings, 2 in the first principal energy level, 8 in the second, 13 in the third principal energy level, and then the fourth one just has those 2 electrons on the outer edge there. Now argon, kind of similar start to these two. We have 2 electrons in the first principal energy level, 8 in the second, and then we also have 8 in the third principal energy level. So the Bohr model for argon would have 3 rings around it, 2 dots in the first ring, 8 in the second, and 8 in the third. Now that is the Bohr electron configuration. Now, if you had to write the Bohr electron configuration outright, a lot of you guys might think, well, do I have to write the sublevel configuration in order to figure that out first? Because that seems like a lot of work. And the answer is no. And the referenced periodic table that you were given at the beginning of the year, you look at the symbols of silicon, manganese, and argon, and right underneath the atomic number, is the Bohr electron configuration. So you'll always have that at your disposal. Just remember and make sure you have this in your notes that these Bohr electron configurations are electron configurations in the ground state only. If they were in the excited state, it's possible that some of these electrons would jump up into a higher energy level, and so they would have a much different electron configuration. These are the ground state electron configurations for silicon, manganese, and argon. Now that we know about how to draw the Bohr configuration, we're going to go back to the sublevel electron configuration. That's that 1s, 2s, 2p, and so on and so forth. And we're going to draw what's called an orbital filling diagram. Now, an orbital filling diagram is a diagram that shows how many electrons an atom has in its occupied electron orbitals. So remember, we might say, like, we have 3d7, meaning we have 7 electrons in the d sublevel, but the orbital filling diagram actually tells us more information because it tells us which orbitals those electrons are actually inside of. So electrons are represented by arrows when we put them into the orbitals. And remember, we still follow the Aufbau principle. However, we also have to follow another rule called Hund's rule. Now, in Hund's rule, that states when electrons are placed in a set of orbitals of equal energy. So let's say that pretend that this is a d sublevel. It could be the 3d, the 4d, doesn't matter. And we're placing electrons in this set of orbitals when the d has 5. The orbitals of the sublevel, the order of the filling for the orbitals is such that each orbital of the subshell receives 1 electron with the same spin, which is going to be an up spin, before any orbital receives a second electron with a down spin. So if I was going to put 7 electrons into the d sublevel right here, we would actually place the first one as an up spin arrow. Okay, and usually you'd find that on Google or in a chemistry textbook, these arrows are actually drawn as a half arrow, and that's kind of a throwback to something called quantum numbers. The spins are assigned a positive 1/2 and a negative 1/2 number, so scientists usually write a half arrow to kind of show that we have an up spin +1 quantum number there. So there's 1 electron with an up spin in the d sublevel. There's another one right next door to it, and then here's the next one, 4th, and then the 5th electron. Now it's important because in Hund's rule, the orbitals are going to fill with an up spin arrow in each one because electrons don't like to occupy the same orbital if they can help it. They're negatively charged and they would repel each other and not want to be in the same orbital. But once we have 1 electron in each one of these orbitals, to actually put another electron in the d sublevel, we would have to have a down spin arrow to pair up with one of our up spin arrows. And if I wanted to draw another one, well, we'd have to draw another down spin arrow like that. And we would keep going. If we had an 8th, 9th, and 10th electron to put in there, we'd have to have down spin. But if we only had 7, this is what our d sublevel would look like. And we would have 2 orbitals that have paired electrons inside of them, and we have 3 orbitals that have unpaired electrons. And this is the arrangement that they would have because this is the most stable electron configuration that you can have because each of these electrons would like to be in their own orbital if they could, but once we had 1 upspin arrow in every single orbital, then they'll start to pair off. And if we had an 8th one to put, we'd put a down arrow here, 9th one would go here, 10th one will go here, and then once the d sublevel is completely full, we will go to the next sublevel in the Aufbau diagram and fill up the electrons in that fashion. So I'm going to show you what that looks like for the first couple of atoms on the periodic table. Lithium has 3 electrons total, and this is a picture of the different sublevels we have following the Aufbau diagram. If you follow the diagonal rule, it starts out with the 1s, then goes to the 2s, then goes to the 2p, and you'll notice there's 3 boxes underneath the 2p here because the 2p sublevel has 3 orbitals inside of it. And then moving from the 2p, we go to the 3s, which would have 1 orbital. So if we wanted to write the electron configuration for lithium that has 3 electrons, following the diagonal rule, it would be simply 1s2, 2s1. So the arrangement of electrons in the first sublevel here would be completely full. We have a 1s2, so there'd be an up spin arrow and a down spin arrow, and that 1s would be completely full. Then the third electron here, that's in the 2s, would just be an up spin arrow in that 2s orbital right there. If we have beryllium, which has 4, well, that's electron configuration is 1s2, 2s2. And so we would have, again, paired electrons, 1 up, 1 down in the 1s, and then we would move to the 2s. And again, it's got to be 1 up, 1 down. Now, when you go to boron, carbon, and nitrogen, which is number 5, 6, and 7 on the periodic table, well, boron has an electron configuration of 1s2, 2s2, 2p1. So the way the electrons go is, well, we got them paired off in the 1s, paired off in the 2s, because that's completely full. But now we have these 3 orbitals in the 2p. So this one electron would be an up spin arrow in that first orbital box for the 2p. When we move to carbon and we want to add another electron, well, that's 1s2, 2s2, 2p2. And so just like boron, we'd have the first 1s and the 2s completely fill, but now we have the 2p sublevel, and since there's 3 possible orbitals of all the same energy there, we would have an up arrow in 2 separate boxes. And then for nitrogen, which adds 1 more electron than carbon has, we would have 1 up or electron in every single one of those boxes. Now, if we move to number 8, we would start pairing them off then. Then we'd have to draw a down spin arrow down here. And then for number 9, we have to put a down spin here. And then for number 10, which is neon, which is our next example right here, that's when we would be completely full of electrons right there in the 2p. And then once this 2p sublevel is completely full and we want to add another electron like we have in sodium, remember according to the Aufbau diagram that goes to the 3s. So the last sublevel here is 3s1. So it would look exactly like neon except in the 3s we would have an upspin arrow, and it just keeps repeating from that over and over and over again as you keep adding them on. Just follow Hund's rule, and remember if you have p, D, or F sublevels that have multiple orbitals inside of there, you have to put an upspin arrow in each one until each box has its own upspin arrow. Then you start pairing them off until they're full. Once you're completely full, you move on to the next sublevel and fill up electrons there. So here's some practice. I highly recommend that you actually shut off the flip lesson right now, or just kind of pause it and see if you can do these yourself in your comp book. But we have silicon, manganese, and argon. Boy, those should start ringing a bell after a while because I showed you the Bohr electron configurations on these earlier. So for silicon, if the first thing you might want to do is pause the flip lesson at this time, see if you can do them yourself. And now I'll give you the answers to what we have here. For silicon, it's 1s2, 2s2, 2p6, 3s2, 3p2. So the way we would set things up is, well, we can write the shortcut here of neon 3s2, 3p2. And I highly recommend that you actually do write the shortcut method for when you're writing orbital filling diagrams, because if you got really large electron configurations like for thorium or for uranium or something like that, which have, well over 80 plus electrons, sometimes 90 plus electrons, it can get kind of cumbersome. So it's a good idea to write the shortcut, and we only have to really draw the arrows for the tail end of the electron configuration. So that's what we're going to do. And so the 3s would be completely full, one box representing one orbital, and an up arrow and a down arrow paired off. But then the 3p has 2 electrons in there. Remember, there's 3 orbitals, so you have 3 boxes that you draw, and then you have an up arrow and an up arrow. For manganese, the shortcut would be argon, 4s2, 3d5, and so you put the little argon in square brackets in the bottom. The 4s has 1 box completely filled with 1 up arrow, 1 down arrow. And then the 3d has 5 electrons in there. But remember, the 3d has 5 orbitals, so there'd be 1 up arrow in every single one of those boxes there. None of them are paired off because we have 5. If we had 3d6, then we would have to pair one off in that first box right there. And then argon, similar startup to silicon there. We got neon. It's 3s2, 3p6 though. So unlike neon here, the 3p is completely full. So we draw neon in square brackets in the bottom, 3s with 1 up, 1 down arrow, and then the 3p would have 3 boxes with paired electrons all the way across. And so that ends our flip lesson on how to draw the Bohr electron configuration and also how to draw orbital filling diagrams.